Welcome everybody to the first DSG seminar of the semester. So it is my pleasure to introduce Hannah Best, who is a full professor at University of Freiburg. From her bio, she developed an early love of programming and math, so she went to theoretical computer science, but she wasn't happy doing art for art's sake, according to her bio, so she came back to work on more practical stuff instead. So along the way, she's worked for Google, been a dean, been a member of the AI Commission for the German Parliament. I met Hannah myself a few years ago because we had a sheer interest in reproducibility, which her talk will touch on today, but primarily she'll be presenting on SPARQL querying. So Hannah, please take it away.
Thank you, Jimmy. So can you all hear me well? If you want to show me a few videos, it would be nice, but I don't know what's the... Yeah, if I can see a few pictures, would be great. So my talk is, yeah, thank you. It's about the clever SPARQL engine. Please tell me anytime when you have questions or problems with sound or anything. Let me talk a bit about RDF and SPARQL first. RDF is based on a strikingly simple principle. All data, whatever it is modeled as triples. Think of it as simple sentences. So here's an example of a few very simple triples. Canada, the capital city is Ottawa. Ontario is located in Canada. Waterloo located in Ontario. You can also have strings, but only on the right side. There's even some type system. You can also think of this as a graph. So if each thing on the left or the right is a node and the things in the middle are labels on the edges. That's why you have this symbol RDF here. It's can you see my mouse pointer when I'm pointing at something? That's great. So it's the number 3 and also the graph is in the symbol. Okay, so these things here in these brackets, angle brackets, are called international resource identifiers, IRIs. That's really just a URL as you know it from a browser, except that you also allow funny characters like German umlauts and all the Unicode characters. So typically the IRIs, which you have in knowledge graphs in RDF, are not human readable, but they rather look like this. For example, the University of Waterloo in Wikidata, I will talk about Wikidata in a second, has this universal international resource identifier. And here are some example triples in Wikidata. So for example, this thing has a name. So the name is not readable. So you need a predicate to say which name it is. Actually has a name in many languages. Here's the French name. Here you see the language tag. There's a triple with these 3 cryptic numbers. What does it mean? It means University of Waterloo. This is the country, and it means it's in Canada. And this says University of Waterloo has coordinates, and these are the coordinates. And here you see a type. So a very simple principle, and as we will see, very, very powerful. Here's some RDF data sets. So one, maybe the most used one is Wikidata. This was successor of Freebase, the knowledge graph which Google bought in 2010, which since then has been integrated into the search engine. They bought it essentially for nothing back then. Wikidata has 18 billion triples, so not million, billion. And as we will see in a second, that's quite a lot and not so easy to handle. Just a few more examples so that you get a feeling of the breadth of data available. And these are not just data sets, they are whole organizations behind this. Organizations, 10 decades of work and dedication and effort to create and maintain these data sets. This is crowdsourced. UniProt is everything biology, proteins, 94 billion triples, 94 billion, that's just huge. So there's a monthly build of the data set. So just building a new version of the data takes a month. There's PubChem, everything about chemistry, 124 billion triples. These are very well maintained data sets. OpenStreetMap, all the geodata of the world, streets, buildings, everything you see on maps, 11 billion triples, also crowdsourced. DBLP, a project I'm also involved in, all literature and computer science adjacent field, 1 billion triples. We will see all these later in the talk. Many more data sets are available as RDF of very high quality and, as I said, maintained with great care. The standard query, how do you query this data? The standard query language is SPARQL. This is the symbol for SPARQL. It's no coincidence that the name sounds similar to SQL because it's really a variant of SQL. SQL adapted to the simplest schema. In databases, you have tables with arbitrary number of columns, and the columns can have arbitrary names. In RDF, you have 3 columns, and it's just subject, predicate, and object. So here is, let's look at that SPARQL query while I take a sip and look at what it does and try to understand it. And so how does it work? In the SPARQL query, in the SPARQL query, you also specify triples, but you just leave some places blank. So you put variables here. And if you put the same variable here, it means it has to be the same match. So this here will show all matches for these 3 variables, title, author, year, so that every triple you see here of the 3 exists in the database. So what it effectively is, it's quite easy to see. It's all papers in DBLP published before 1940. And let's just have a look. Here, this is our SPARQL engine. I will talk more about it. I just execute the query here. And you see I get 70 publications, not too many. You will see most papers at the time were single authored. Let's look, I think there's 1. And let's also look at some author names. I can add the label predicates automatically here. I think there's 1 paper. Let me scroll down a bit here. Yeah, here you see 1. So if you have a paper, let's just go back. This is one important thing about SPARQL. If the result is always a table. So if you have paper with 2 authors, the paper and the title will be repeated. That's the only way you get a table here, right? So here for new foundation of formal meta-mathematics, you have 2 authors, Vladimir Hedber and Leon. And if you click on here, so it's like a URL, you get the entry in DBLP. So these are also like URLs, these thingies. Okay. So you may wonder if you have heard this for the first time, since it's just database stuff. In theory, yes. In theory, you can also read a paper and the binary representation of the PDF. RDF data can be stored in a database, and you can just translate SPARQL to SQL. And actually, some engines do exactly that, but it's not the best way to do it. But maybe there are lots of small differences. The maybe biggest difference is interoperability. If you have ever worked with databases, more complex data in databases, interoperability is just a nightmare. Even if it's the same kind of data, 2 people have slightly different schema, it just, bottom line is, it doesn't work. RDF and SPARQL are made for interoperability from the ground up. So all you need, here's an example, and we will see these data sets in more detail in a second. You have Wikidata, which is general purpose knowledge, OpenStreetMap, which is geodata of the world. So all you need is, so here, this first triple is from Wikidata, and it says the population of, this is actually not quite true, 183 is Germany, never mind. The population of Germany is 83 million. And here it says, in OpenStreetMap data, this ID in OpenStreetMap data corresponds to this ID in Wikidata. In an OpenStreetMap data, you have the geometry of Germany in this case. So this is wrong, what's written there. I just didn't change the example. So all you need is a triple saying this entity over here is this entity over there. And you can have it in either data set or both. And voila, you have combined the data set. And it's really, you need to do nothing else. really just do cat on the command line. You concatenate the two input files and it works. And that's just, and also everything query optimization in SPARQL is a different game. Now let me just show you some example queries here, and I need your help. So let's see whether clicking on this works. So I want the first name, please, and maybe one that is not super infrequent, but otherwise it's your choice.
Jimmy.
Jimmy. Okay, let's look at Jimmy. Here's Jimmy. And what I now get is all people, Wikidata knows where the first name is Jimmy. And let's just look at a map of their birthplaces. So Jimmy, as we can see, is quite a popular name around the world.
Is Jimmy Lin in that list? Can we tell? I'm looking to see if Jimmy Lin.
Yeah, if we know his birthplace, we can find it out, but maybe you can ask that in the questions. We can locate him. He might be, I'm sure, if there's a Wikipedia article about him, he will be in the list. Okay, the next query, just to give you a feeling for what's possible. This is everything that happened today, some years ago, on this date today, 1910. So we see Belarus was founded on September 19th. It's the burial of Queen Elizabeth. You see this data set is super up to date. I'm surprised myself. It's the death of Virgil. That's, I think, a Roman poet. Hesse, that's a state in Germany, was founded, and so on. And this is 18,000 hits. By the way, you should see that everything goes rather fast. Let's go more queries. Maybe skip these two in the interest of time. Oh, that's a hard one. All streets in Canada. All streets in OpenStreetMap in Canada. That's a lot. Let's see how fast that goes. Okay, that's 5,400,000 streets, only showing 100 here. Let's look at them on a map, shall we? How do we display 5 million things on a map? Well, there we go. Let's zoom in. So we see heat map-like thingy here. It's a funny distribution in Canada because you don't have many, you do have some streets.
This is awesome. That's the best population density map of Canada I've ever seen.
Yeah, it's streets. It's not buildings. It's
I know, but it's like this. It is a population density map, 100%.
Yeah, in a sense, streets is measures density. I also like the streets view. And you see, you can zoom here all the way in. And if I click on something here, I actually get, it's always real things in OpenStreetMap. So it's this thing. Somebody entered this funny shape 1 year ago. A street lover. OpenStreetMap is also crowdsourced, right? Let's take another one. Oh yeah, that's a nice one because it combines two data sets. And as I said, that's baked into RDF SPARQL. So let's just look at all countries of the world where Spanish is the official language. Countries in their shape, it's an OpenStreetMap. Official language is in Wikidata. As you can see, there's just a way to specify this in with this. So you just say, okay, this part of the information, you should ask that other endpoint.
Can you change it to French? I'm just curious.
To French?
Yeah.
Yeah, this is live.
Uh,
So you want to change it to French. Et voila.
yeah, okay, yeah.
Looks good, right?
Yeah, all of Canada.
All of Canada. Yeah, it just says this country has, as that's how it's.
It is.
It's not in Wikidata. And maybe a last one, and then we go on. This is all public. Oh, it's the average number of authors per year, how it decreases per year. Let's go back to, that's in DBLP. So in 1936, the average number of authors per paper was 1. What is it today? It's 4.04, and it's increasing. It's ever increasing. So the point of these queries was to just show you the enormous variety of data. And also that's super important. I did not set up very specific demos for all these queries. This was one and the same system with very little configuration. You just take the data that's there and you can do it. And also the things I'm going to explain in the following, you can just do them. And that's just yeah, if you have more experience with this, you really value this. Finding the right SPARQL. You have seen the SPARQL queries. I've just shown them to you very quickly. It's not so easy. So here's a simple example. Looks like a query you might type into Google. The Oscars of Meryl Streep. She won 3 Oscars. And I also want to know the movie. So that's the result I want to get. A note. So she won the Oscar for Best Actress twice, but for 2 different movies. The other one was Best Supporting Actress. Okay. So there's really one way to ask a SPARQL query properly, and that's the SPARQL query in Wikidata. And the principle is easy. It's just triples. But you see, I mean, first you have these IDs here, you have this prefix definition. Let me explain these prefix definitions. What it means is, if I write P colon here, it means just use this thing here as the URL prefix. That's all there is. Just like namespace abbreviation. So how on earth can you construct this query? Let's just see. So what's hard about this? So first, you have to know these prefix definitions, but that's easy. A program could do that for you. Then you have to know the right entity names. It's about Oscars for Meryl Streep. You have to know that Oscar is really called Academy Award, that it has this ID. Meryl Streep is 873 in Wikidata. This one is really hard, even for super experts. You couldn't do it without help. You have to know there's a predicate, won award, and there are 2 variants of it. It's called P166. Why do you need that? Because it's all triples. Here you go from Meryl Streep to an object which stands for a particular award. And here you go from the object to the award. And here you go from the object to the movie. You need an intermediate object because you just have triples, right? Think of it, you have in a graph, you want to attach several things to one node. You need some intermediate node. So you're going to that node, and then there are a number of edges going from that node. So let's just look at what tools are out there, and let's just take the Wikidata query builder, and let's just try to. So this is Wikidata query service is used. I think, I don't know, 10 million hits per month. I mean, it's used a lot. People build, they do not only ask queries, they build whole web services and everything on it. Let's try to construct this query. So control space, you get some auto completion here. Now I want to start with Meryl Streep. Let me try. Okay, this doesn't work. What do I have to do? I actually have to know the prefix. I have to know that entities start with WD, Wikidata. Now I can do auto completion, Mary is not enough. I need to type Meryl, and then Meryl Streep is down here. Let's go on. Now I need award, but I need the P colon thing, which means the only way to continue is if I type this. And this is essentially something I have to know. There's just no way I can guess this, right? And now I can type something like award, and I find this, and now I get, now I can type, this is my intermediate node. Now I need to know this. And now I need to know, how do I get to the movie? Now I need to know the right prefix and how to get to the movie from an award. There's just no way you can guess this, which means even for this relatively simple query, you are done here. Let's look at our query builder. So far, I haven't shown you how to construct queries. Let's just go to Wikidata here and just very quickly. So that's 17.5 billion triples. That's a really big data set. Let's just see how it works. So it starts like this. Okay, now it suggests subjects. So let's just type Mary. I type Mary, I get Meryl Streep. She's fairly popular, so that's not too hard. Now I get predicates. I'm now at the position of a predicate. Actually, award received is already here without typing anything because it's Meryl Streep. What predicates does she have? I mean, awards is one of the prominent ones. And here I see I have a choice. So I have to know I want to go to the intermediate entity. So I just pick this one. Now I already see I get to these funny intermediate nodes. They have these funny names. I'm not interested. I just take this variable name, Meryl Streep. So this now stands for a particular award by her. Now I type this. Now I'm in the next triple. See, now my choices are very limited. I'm now in the world of awards of Meryl Streep. So what do I want? I want the award. I can see there are several of them, but I don't want a specific one. I want a variable. What else do I want? I want the movie. Which one is the for movie predicate without knowing anything about Wikidata? Somebody listening? I don't hear you. Charlie, you are muted in case you're saying.
We have no idea.
For work?
Yeah, for work, I think. I mean,
For work. Okay.
for work, I guess. Okay, and then I want to say it's an Oscar. And I'm not even typing anything for the predicates, right? It's already in the, and so here I have the kinds of awards, Academy Awards. Okay, and let's just see, what do I want? I want the award and the work, and voila, I get them without name. I can automatically add the name triples here, and I get the result. So I needed to know. And that's huge, what you just saw. So the suggestions come as you type. There's no unnatural interface like typing a query first, and they are context sensitive. So they are sensitive to what you have already typed, which means it narrows down very quickly, which is what you basically have for every SPARQL query. You need to know, of course, how SPARQL works basically, but not much more. How do you compute these suggestions? I won't go into much depth, but a little bit. Funny thing is, these suggestions are computed themselves via SPARQL query. And let me show you on exactly the same data set on which you're formulating your query on this and asking the same engine.
I'll note there's somebody with their hand up, right?
Oh yeah,
Emil?
I don't see any hands, but so please do ask.
Oh, okay, now the hand has gone away.
I can ask the question, I had a question. Can I ask?
Yeah, can I see you? Then I understand the question better, I think. But you can also ask.
Sure. Yeah, here I
Yeah,
am.
hello. Nice
Yeah.
to see you.
Yep. So my question is that when you were writing the queries, how did you actually know the order, like which one to come first? Because all are coming from the internal, right? You are not
Yes.
typing. So how would
Okay,
you
this
decide the
question will
order?
be a very good question. Great question. It will be answered on this and the next slide. So it's a very appropriate question. Here's, so for example, so we are asking queries in SPARQL, the same language, using the same query engine to get the suggestions. This is quite, think about it, it's a really nice idea. And now we are trying, and of course this only works, this is a huge data set if these queries are efficient. It turns out that these suggestions, these auto-completion queries, they're kind of SPARQL hard. So if you can do them fast, you can do everything fast. That's also really nice. So it's not that you're doing some super specific tuning here. So assume we have typed this. So this is this means instance of in Wikidata, this means human. So we have already said this variable is a human. And now we type the next triple. And now what do we expect? Now we type the subject, now comes the predicate. Now we expect properties of humans like gender, profession, and date of birth and place of birth and stuff like this. How do we get these suggestions? Well, this is the query we ask. And let's just look at it on QLever. And let me just, so let's first look at what the query computes. That's what it computes. It computes exactly this list. So the first one is instance of. So maybe I want to add another type predicate. Yes, this is a person, but also this. Here's the score. I get gender, occupation. How do I get it? And that answers your question. I'm just putting here, okay, let me look at all triples associated to all people. That's what I'm doing here. These two lines here give me all triples associated with all people in Wikidata. And now I just group them by predicate. And then I count how many distinct persons do I have per predicate, which means I get those predicates first, which a lot of people have, which is probably what I want. And this kind of ranking you can do for the other fields too. You just do it per frequency, and you just do it with a pretty basic SPARQL query. So that's how you do it. Here's the result, and you get, and this ranking turns out to be, it's a very simple ranking, turns out to work great. For the example I showed you, I had to type super little, and that's actually pretty common. The problem is that's a very hard query. This is all triples by all people, and Wikidata is huge. There are 400 million of them, which means this query has to touch 400 million thingies in my engine. How did it do that? It took, it says, maybe I should, let me clear the cache to see, okay, it took 1 millisecond. How does it do that so fast? That's, and by the way, I can here go to the other, I can go to the Wikidata query service and try the same query. We don't have to wait because it will never finish like most queries on the Wikidata query service. Just very quickly, the idea here, if you think about what's in the database and think about persons, let's only talk about persons, most of them will have the same or very similar set of predicates. So most people will have gender, profession, date of birth. So to store that information, you don't need to store the whole set. You can just say, okay, here's a set typical predicates of persons, and I'm just storing that tag with that person. So that's the basic idea. Mathematically, it's this problem. You have a set of sets. So it's just a set of predicates of each entity. And now you have a set of patterns, just frequent patterns that occur in this set. And then you want to compute patterns such that you can write each set of predicate as a disjoint union of very few of these patterns. And that's the problem we solve, and that gives you the result we just saw. Would love to go. I could give a whole talk about any of these small problems, but I opted for an overview. And please do ask if you have any questions. So what you saw was QLever. It's also in the title of the talk. We very briefly talk about QLever. So what are the design goals? We want to solve 100 billion plus triples on a PC with standard hardware. This was not running on a huge cluster. This was running on a 64 gig machine for 1,500 euros. We want to profit from, if you have solid state disk, great, you don't need it. If you have more RAM, great, but you don't need it. It's pretty important for a research group because you have a new student, if they need their whole cluster to set up an instance, that's a problem. We want it to be maximally fast for all the typical but notoriously hard queries written in modern C++. I should say from the ground up. So it's not using some other database. It's basically a whole database system written from the ground up, of course, open source. And we want it not to be some half-functional research prototype, but something that works and survives generations of students. That's a challenge in research environment. Let's look performance. Okay, yeah, Grant, it's perfectly okay to ask a question. I'm happy about questions.
Just a high level one. I guess you're familiar with something called RDFS.
RDFS?
Yeah, RDFS adds an interpretation to predicates like instance of and subclass of and so on.
Yeah.
I'm just curious if that's underlying your automatic query composition thing. Are you assuming that you have RDFS?
That's a good question. But for example, here's an example query which shows that it's just something you have to be aware of. So for example, I want city, and if I do this, I want everything that's a city. I will not get all cities. Why? Because in Wikidata, some things are big city, and then big city is a subclass of city. So you have these chains of things leading to city. So what you actually have to ask, and you see that the Auto-completion will help you. Here, you want this, you want instance of and any number of subclass of and then city. And this, by the way, is a very hard query, which is why it takes a little longer. And Blue says it did some approximation thing here. And now you actually get all cities. So, but that's the thing is, there's no magic happening here. You are just writing, and that's deliberate. You are just writing SPARQL. You're not. It's not taking things away from you that you don't see, like so many other query builders, which do some magic, but you don't understand it. You get exactly SPARQL. That's a predicate.
So that property is like a regular expression that says, go over any number of edges that are subclass of. Is that
yes,
right?
if you see exactly the mouse over, this predicate is instance of, and this is subclass of, and this expression says instance of, and then 0 or more subclass of, which means you can traverse type hierarchies, which is key. You need it in every second or third query because it's so. So yes.
Can you run that?
Can I run that?
Yeah.
No, that's too hard. Yeah, it took 215 milliseconds. Sorry. Yeah, so it's 56. Yeah, of course you can run it.
Yeah.
You have to try hard, I think, and you need a distinct here for technical
Boston
reasons.
a bunch. Yeah. Well, you had a bunch of Bostons, right?
Yeah.
Yeah.
Okay.
So just a comment that if you supported RDFS, then the transitive closure of subclass of would be inferred. That is to say, subclass of is a interpreted middle thing, predicate that the RDFS standard would say mandates the inference that you've hand encoded there with that transitive closure.
Yeah. There was a comment or a question?
Just a final comment. No more questions.
Yeah.
Sorry.
Okay. Thank you. So let's look at two other engines, and not any two engines, but the two big ones. So one is BlazeGraph. That's the engine behind the Wikidata query service, which is used a lot. It's like Wikidata is the fastest growing Wikimedia thingy for a while now. And it's getting huge. Unfortunately, the whole team was acqui-hired by Amazon in 2018, and BlazeGraph is hitting some performance problems. And it's written in Java, that's also a problem. There's Virtuoso, which has been around for a long time. This is very widely used. We will talk more about these. And then there is QLever, which is kind of new kid on the block and quite a bit faster than these other engines. And I'm not sure, maybe I should, yeah, I can just click on these queries. Here's just to show you by a very simple example what's hard. This is just 10 random people. It just says limit 10 here. And people in this world are actually used to write limit. Now this is easy. This just says, give me 10 people and their English label, and that's it. So the database, the SPARQL engine can choose. So this is fast. Even if I go on a Wikidata query service here, it will give me 10 people. It will give me 10 different people, but it will give me 10 people. So that's an easy query. Here's another one, more typical. Now I want the 10 queries with the most links. Let's look at that query and understand why this is much harder. So this is now, person, instance of human, a label, and now I have a triple saying, okay, here's a link to that person. And a link in Wikidata, Wikibase, can be a Wikipedia article, can be something linking to that person. There's a triple about it. And now I'm just grouping and counting for each person and the name, how many links do I have? Let's do that query with our engine. You see it takes a little longer, 3 seconds. And here we have the top 10 people in Wikidata. Barack Obama, followed by Jesus and William Shakespeare, the usual suspects. So it's just 10 hits, but to get these 10 hits, you had to do a lot of work. And if I Yeah, we can run it, but it's no, we can also do Virtuoso for a change. This is Virtuoso, looks a bit old-fashioned, and yeah, we don't have to wait because it's just too hard. This query is just too hard. It has to look at the whole data. To be precise, 187 million things you have to look at, you have to aggregate, you have to sort. Sorting that many items is also not easy if you want it fast. So more generally, so BlazeGraph, it's in Java, hence slow. It's a great reference engine. I mean, it was a professional company, adheres to the standard very closely. Virtuoso is kind of this older generation thing. If you look at it, it's in C, undocumented C, which means it's basically not maintainable anymore. They both struggle when a query requires touching large parts of the data, even if the end result is small. And this is the typical case. It's not the exception. And let me just show you this here, because I think, so Wikidata, this Wikidata has problems right now. So you see here, they're speaking of catastrophic failure of the query service. And it's not only a theoretical possibility. So they are saying its probability is very likely that it will occur in the next 5 years. So you see 17.5 billion triples, and they have quite a bit of hardware and everything. It's not easy. So they have a playbook, what they do if everything crashes and nothing works anymore, because so much ecosystems rely on this. So what they did, they are looking for a successor engine, and the market is huge. And so they have this engine. So here are the big five, like there's a BlazeGraph currently in use, there's our engine, there's Virtuoso, and then there are these two Java engines. Let's just look at 2 lines, because I find these particularly interesting. Scalability, you only have QLever written in C++20, our engine, Virtuoso written in C. So Virtuoso is fast. And now let's look at this. Well-designed and documented code base. So we are talking about something from research here. So QLever has a 5. That's quite amazing. Virtuoso, this company, market leader in their field, has a 2. So yeah, I think these are quite amazing numbers.
So where are you, like it's good that you're awesome in these particular categories, but where are you falling short of the commercial?
We are exactly falling short in one thing. I mean, we have started to work on this with a relatively small group, maybe 5 years ago, which means some things are just not yet implemented. The SPARQL standard, but in no other respect do we fall short. But for example, you see here, actually, it says here star, 0 star. We will do federate. Actually, you have seen federated query in one of the examples. It was this service clause. But I have told them already, I mean, we left the simple things. The hard things we did, but there's a lot of stuff you just have to do, which is work. But there's not really something left where I would say, okay, that's hard.
And what is support for read and write at high frequency?
I think these are very special things. You have to understand that this report was written from their perspective, and that's a maintainer perspective, not a developer perspective. So it's things where we say, yeah, no problem, you can have that, just takes us a while, but for them it's important. So that's not really a thing where we would say, okay, that's challenging, but it is work, and we will do it, we want to do it. Jimmy?
So whenever I hear, oh, it does everything, I'm immediately skeptical. So what you don't get anything for free, right? So what are the trade-offs that you're making? Is it a time for space? Is it being clever in the algorithms? I mean, it's always got to be something, right? There's got to be a secret sauce. So can you elaborate a little bit?
I don't think so. If you're just talking about, I understand what you're saying, but we are talking about a SPARQL engine, which is good. Look, these companies are also selling other products, right? So they're in this whole knowledge graph business. I don't know what they are doing. Knowledge graph databases, that's a people have all kinds of needs, what they want, maintaining their data, constructing their data. We are just in the SPARQL engine business. And there, I think it's just strictly greater than all these engines. And these engines, these are big community products. They're written in Java. And if you're written in Java, I mean, you usually get clean software, but it's just slow. There's no way. So basically what we are doing, and I will have a slide on this, we are just doing everything right. So it's actually quite simple. So it's just all the other engines have stuff where you say, okay, that was a bad decision. You shouldn't have done that. And Virtuoso can't change that it's written in C and undocumented and hard to develop further. I mean,
so just a quick question. Update speed is okay, so you're not sacrificing the update performance.
Yes, this is one of the things we still have to. That's correct. That's a good one. What we cannot have is transactions at such a rate that the whole database changes in. What we can support is you have the 17.5 billion triples and 1 million triples drop in the next minutes or so, which is the typical use case. So yes, this constraint is there, but every data set I've shown you, the bills are like daily, weekly, or monthly. And
So
yes, this is also something we need to do, but it's not an algorithmic problem.
So
yes.
practically, sorry,
Yeah.
I was going to
Yes,
say
go on.
practically for the things that you're targeting, you do not need to have huge numbers of simultaneous transactions and things like that. Okay.
Oh yeah, and we don't have transactions or anything like this, right? It's not, it's just things coming in and then you update. We don't have atomic but you don't have that in the RDF SPARQL world, really. Grant, do you have a comment or question?
Really, just another. All my questions are high level. Architecturally, when your system gets a SPARQL query, do you go through a first phase where you compile that into a query plan and then a second phase where you execute that query plan?
Oh yeah, absolutely. I haven't shown you that yet. So if I go to this query here and I click on analysis, you get the query plan. So here you see what the engine does. And it's on this level, it's pretty basic stuff. So here you have an index scan operation, something that was pre-computed. You scan it. Scans are very important. So here you scan 10 million items. Here you scan another index. So these are things sorted in particular orders. So here you are joining 84 million and 10 million things. And it's done in 400 milliseconds, which is very fast. So simple join is something where you can lose a lot or do a lot of things right. I have a slide about that. And here you can execute queries yourself, click on the query plan and see what's happening. And this is actually a very important tool for our development.
Those cumulative times, because
these are not cumulative times, no.
So the overall thing took a couple of seconds, right?
This was, I think, the hard query. Yes, this was the one which took 3 seconds.
Yeah.
This is the one which looked at all links of everybody. And so this was not easy. And you can see why. It has to look at all the links, all the people, intersect this, and so on. Hard query. And you don't know which queries will come. So I have one quick slide. Yeah, go on.
Just one quick follow on. The nodes at the leaves of that tree sort of correspond to a selection of indexes. Does your system change its mind about which indexes exist and so on based on query workload, or is there any facet of
no, it just does query planning. So it considers a lot of possibilities. It's not even the fancy part about QLever. So query planning turns out is not so, it's important, but it's not where most of our work goes. So you just compute all kinds of query plans, then you have estimates. Here you see in square brackets, it's the estimates of the result size. And then you just take the cheapest one and then you go with it. There's room for improvement here, but so far query planning has not been our bottleneck, interestingly.
Thanks.
Oh yeah, very welcome. So I could talk a whole semester about everything behind. Okay, I think, stuff to finish. Yeah, I can stop at any time, of course. This is important. So I have some high-level messages which I want to bring across. So maybe I go to these. QLever is 80% very carefully engineered strong baselines. Let me say a few sentences about that. And 20%, I've shown you some new algorithms also, like this thing with these patterns and sets and covering and so on. It's 80-20. So some of you may think only 20%, so that's not very researchy. Okay, 2 comments here. One is engineering a strong baseline. So first making it a strong baseline, then implementing it such that it's really strong. That's hard. You have to know the algorithm, you have to understand the hardware, the programming languages, and how the three interact. Can't tell you how many implementations I see where I say, okay, that's very far from optimal. There are lots of potential for improvement. And also, it's not easy. I mean, in research, we're used to always go for the new fancy algorithm with deep theory behind it, but it's actually a hard problem to know, okay, this part, can I go with a baseline or do I need a new algorithm? So this decision, this or that, is also a hard one. And you have to understand a lot to make that. And very often, 4 out of 5, it's better to take the baseline, but you have to make the right choice. Okay. I think, yeah, let me just, I also want to show you this. Let me just, okay, so you say, yeah, this is a research prototype. This will be terrible to use. Let me just make one. Okay, let me just, so this is cloning QLever from GitHub. And it's actually not cloning the whole engine. It's just, so now it's essentially just cloned a script and some config files. Now let me just make a directory here. Let me go there. Now let me go to what I just downloaded. I get some help here. And what the help tells me, okay, I should set it up. I set it up like this, and I take a pre-configuration Olympics data set. It's everything about the Olympics game. Let me do it. It just happened. And I'm doing this on a machine where there is nothing else. I now have a configuration file which says everything, how much memory to use, on which port to run, what's the name of the data set, and so on. I download the data. Now I have the data. It's this NT file. It's just a text file with triples. We can look at it. There we go. Let me index the data. Now I index the data. It tells me exactly what it does on the low level, but I don't have to know it. So I just have this high-level script. It indexed the data here. Let me start the server. It started the server. And let me start the UI. So the UI is now running on my machine. And here we go. We have a UI on this data set, which I've just built. I have some example queries here. And I really did this from, yeah, so this is just gold medal winners by number of medals and so on. Ease of use is not just nice to have. I mean, obviously, if you want real users, you should care about this. It's also important for your own group. Onboarding of students, you want students to do projects on this. If they first need like 2 weeks instructions, you have a problem, or a whole lecture. It's also absolutely crucial if you want your software to survive more than one generation of students. Yeah, your super smart PhD students goes away and then it's dead. That's not what you want here. So how much time do we have? So we had a few questions now already. Just tell me and I will plan accordingly.
Well, probably another 10 minutes, Hannah.
10 minutes?
Yeah, probably 10, maybe 15 we can do.
Yeah, okay, 10, 15 minutes, it's perfect. So let me briefly talk you about GeoSPARQL, just because it's so fancy. That will be quick. So in GeoSPARQL, you can just specify geometry information, which is points, lines, and polygons and multi-polygons, things with whole basic geometries. There's a standard about this. There's a whole consortium defining this. And then now you have triples of this kind, like saying, okay, Ontario contains Waterloo, your Waterloo. Ontario intersects, phone, I'm not talking to you. Ontario intersects the Ottawa River, and so on. So you have these geometric relations, and you also specify them with a triple. And let me just, okay, Baden-Württemberg is the German state I live in. Let me just show you two more example queries here. That's just all post boxes in Baden-Württemberg, quick 10,000. Let's view them on the map. Here they are, all post boxes in Baden-Württemberg. So if I click on one here, I go here, I get the post box somebody entered in OpenStreetMap. How about all buildings? We already saw a similar query before. All buildings in Baden-Württemberg, in my state, it's 10.5 million. Okay, that takes a while, but it's 10.5. And now, by the way, every action I do here is a query. I will talk very quickly about this in a second. This visualization is rather sophisticated. So I go in here in some city and I get a building. If I click here, yeah, it's some wash building. Okay. So the standard tool for this, so OpenStreetMap has a tool for this. What people usually use is PostgreSQL and PostGIS, so the geometric extension. And these kinds of queries, which are very natural, give me everything of a certain kind contained in a certain area. It doesn't have to be a state, could be anything, could be a mountain range or whatever. These just take forever. It doesn't work because these queries are very hard. Let me just explain very quickly how they work. So for OSM Planet, you have 1.5 billion geometry objects. And what you want in the database world is a spatial self-join. So you want all pairs of these objects where this is contained in this, or this intersects this. So this is a huge spatial self-join, and you want it on a small machine. You don't want a cluster or something. What's the standard approach? You put the objects in some spatial data structure. Oh, now everybody is leaving. Am I alone now? Or if I don't see anyone on screen, then I'm slightly irritated. So first, for each object, the spatial data structure gives this to you. Give me all objects which are at least in principle in the vicinity, intersecting bounding box. Then for each pair, try a simple check and then do the real check. The problem is these, it's just so many checks you have to do, and you have to do very many expensive. If you compare, for example, to the border of Germany, it has like 100,000 points. It's a very, very complex object, complex in a number of things. It's just very fractal almost. I will skip over this in the interest of time. It's another one. That's a part where you don't go with a baseline. It's just you need fancy algorithms. So what we and you have seen what we are doing, and maybe I want to show you one thing because it's so nice. So here's the problem. So it says on the slide, this is the theory which I've now skipped. Making this work in practice for such a huge data set is another story. So what I have here is all the checks which our pre-computation did. And it's a query. And note what I just did is I just took the algorithm, made it output a few triples, RDF data, and use our own engine to search it. And what I find is that of the 30 minutes which this pre-computation took, and it should only be 10 minutes, 10 minutes go into comparisons with this shape. And let's look at this shape. And this shape is Jutland, which is a part of Denmark. and it takes a while to draw in OpenStreetMap because it's such a complex shape. And the second one, let's also open this here, is I think, yeah, it's Jutland Peninsula. So a lot of objects, 2/3 of the time is spent in comparing objects against these two objects. And actually, here's another query where I can just say which objects these are. And look, I'm using our own engine to analyze the algorithm on this. And now I'm using the visualization. And here I see the problem. So the problem is that all objects in this area, instead of everything that you see here, every small street, every house is not compared to a smaller area as it should, it's compared to the whole area. And these checks, they cost like 2/3 of the time. And I can also tell you what the problem is. And then I go on with my final remarks. The problem is there are these two regions here. So this region here is called Tönder. And this has this funny island or half island, which is connected to this region. And this is Jutland, which does not contain this. So this is not contained in this. So it's only half contained in this. So you have something where you only have a slight hierarchy. And these things happen in data all the time. Now I've shown you the problem. If you look at it, it's always like this. I mean, that's how all discoveries are made, right? If you look at it, then it's easy, but you have to find it. Find this in 1.5 billion geometry object. And it's so nice that our own tools were helpful to find this. Yeah, I showed you this visualization stuff already. And that's my meta part now. Tamer and Jimmy, how much time do you give me for my meta comments? It's not much.
Go for another 5-7 minutes or so.
Mm-hmm. That's perfect. That was my, yeah. So, are other people still listening? I don't see any faces.
No, there are still people.
We don't know what they are doing, but let's assume they are still listening. So practical. Oh, thank you for showing a face. It's so nice. Thank you. So there are rewards of doing practical work in academia. I mean, you get feedback and honest feedback, whether your super nice, fancy theoretical ideas actually work in practice. Spoiler alert, most of them don't. I mean, it's a great inspiration and testing ground for more research. You have a working engine. Now you can try out all ideas, just implement something on top, see if it works. That's just a great. When it's useful to others, it's, at least for me, the greatest joy has always been. Here's some challenges. So you have to understand the theoretical stuff, obviously. You have to understand the data. I've shown you a few examples where it was important to understand the data. You have to understand standards. We are implementing SPARQL RDF standard here, super well defined. You have to understand writing and managing software if you want to survive this several generations of students. And you have to get it published, which is of course easy because everybody loves stuff that actually works, right? I mean, you see this and say, wow, that's great. Yeah, so here's yeah, that's just a simple picture. So you have academia, you have these well-defined problems, rigorous analysis, or at least you try to. It's usually not practical. In industry, you have these very ill-defined problems. Theory is often quite basic or non-existent, but you have actual products, often using algorithms from like 3 decades ago or something like that. And then you just buy new hardware so that it's fast enough. And there's this huge gap in between. And nowadays, when it's bridged, it's usually bridged from industry side because the smart people who like to code, they go to industry. They don't stay in academia. I will come back to that. Here's an example meta review we get for this kind of work I've shown you. So there it is. The paper has generated a lot of discussion. The reviewers agree that the paper addresses an important problem. Great. The solution is implemented, extensive experimental evaluation. All the code, resources, reproducibility are publicly available. Results are great. However, the scientific problem addressed by the paper is not clearly identified. The paper advances the state of the art with an engineering-like contribution without addressing the problem from a more fundamental perspective. So this is my comment to such a kind of remark. Yeah, this is, oh, the arrogance, oh, the arrogance. So let me, just very quickly, what's wrong? Maybe it's right. What's wrong with such feedback? Judge a paper for what it does, not for what you think it should be doing instead. With the exact same logic, you could summarily dismiss all theory work and say, you shouldn't do that. Say, this has no applications, it's impractical, reject. I mean, that's, if it's theory, judge it as theory. If it works, judge it as that. It's so simple, still it's not done. And that's just arrogance. Don't judge relevance. I mean, there are so many experiments about this by now. Humans are known to perform very poorly at judging relevance. Only it's like predicting the future. It's notoriously hard. You might say, okay, I just picked a review here for the effect. That's not true. This kind of feedback is the rule. We get it for our work all the time, not the exception. And I should say, I come from theory. So I've done theoretical work. And so that's particularly strange. How I would summarize it, there's this pervasive disregard of the challenges of getting a theoretical idea to actually work in practice. And the really strange thing is this is coming from people who often cannot code, or if they code, I've looked at a lot of code from researchers, it's a mess. Usability is typically dreadful, and then you just dismiss something which you have no idea about yourself. And I think that's the definition of arrogance, if you ask me. So younger folks like to code, right? So this is going to change. Well, I talk a lot to younger folks about implementing their ideas or building systems. Here's the answer I usually get. One half says, no, I'm not going to do this. This is a lot of work. It's ungrateful. You don't get any credit for it. So don't do it if you want to have a career. I get this answer all the time from people who want to become professors, from young people, this generation. The other half goes to industry. I mean, that's simplified now. Often very smart people who like to code, who are also good at theory, but who also like to build stuff that works, they go to industry, they leave academia. And what's the consequence? This super lopsided situation just keeps perpetuating itself, right? And that's not only a loss, it's also a danger. I think there's danger of academia becoming a bit irrelevant because of that. And you also have that in some areas. It also encourages, you could almost say forces, dishonest behavior, concealing simplicity. You have to make stuff more complex than it actually is. You have to add some fake theory, fake depth, code that only works for a paper, if at all, overselling, and so on. It's all part of this. 2 more slides, then I'm done. Reproducibility, it's actually directly connected. And since we are doing this practical work, we look at a lot of code and evaluations of others. And what we frequently find as code researchers write is just, it's just terrible. Documentation usually does not exist. If it runs at all, there's so little information that you can rarely reproduce it. It's really the exception that you can reproduce the result. So in academia, we have this super highly developed over centuries culture of publications. With respect to writing software, 2022, it's still basically anarchy, right? And how should it be? If you ask me, why not? We have these high standards with respect to publications, and I've suggested that many times. Why not make it a requirement that if it's work that can be implemented, code should be properly written, precise instructions how you get the results, And let me just show you an example. It's and that's my last example, which I show. So here's this paper about the auto-completion. There's a link in the abstract. If I click on it, I get to the paper, I get to a page with a material. And here I have an evaluation, the evaluation result. And let's just, let me just go to the, sorry, now I removed the paper again. There's a table in the paper. And I want to go to that table. That's my last slide, really. Here's the, yeah, sorry. Should have kept that open. And let's just, okay, this is about the auto-completion MRR, some numbers, we don't have to understand them, just remember these numbers, 67, 96, 98, 67, let me just go here, this was one row in the table, 67, 96, 98. So this is just, it's the numbers from the table, the exact numbers, just in an interactive way. So I can click on here, I see the actual queries here. I can click on a query. I can see what happened for that query. I can see the query processing tree. So of course, this could all be faked, right? But this is exactly the experiment which led to that table. You can see exactly what happened for every query. It's something you should just do anyway. And by the way, what you can also do, it's also not hard. You click here, you just get the LaTeX code for the table, right? You take this, you paste it into the paper, you get exactly that table. So that's what I call reproducibility. It's a little bit of work, but if you have done it once or twice, you can just reuse it for papers. So why is this not required? Here, two standard counter arguments are here. Counter arguments, I would call it excuses. One is, seriously, colleagues say this is asking too much of researchers. You can't ask this of researchers, I see. So practical work is not scientific enough, but writing proper code, it's just too hard. It's too hard for the poor researchers. And then you have this proprietary, some people have proprietary data, proprietary code. Yeah, this happens. These are exceptions, and you can deal with that too. The kind of thing I've just shown you is you can also do it completely anonymously, and you get some proof that these were actual numbers. So that's my final slide. So I hope I could convey some of the fascination behind this RDF SPARQL world. Really, I see a lot of people writing scripts, sometimes days, hours, or weeks on doing something where I say, hey, that's just a SPARQL query. Even one on data that's actually there. So think about it the next time when you're doing something like this. You need maybe it's just a SPARQL query, and you can do it in 1 minute and not 3 weeks. Yeah, peer review, I said something about this. Yeah, and I think we need a culture of not just clever ideas, but also writing proper software and having reproducible results. And that's the end of my talk. Thank you very much for your patience, attention.
Are you okay with more questions, or what's your timing?
I would be happy. I don't know if whoever has to run.
I think
Please go ahead.
I think one question was okay, probably.
Well, again, high level, sorry, but I have similar problems with project Dave Toman and I have going on with an evolving software base that's supposed to last longer than the length of time one student takes to finish a master's. And one conclusion we have, hard learned, is you desperately need really good documentation that are not papers, but documentation for your software system. Could you comment, like, how do you get a master's student productive after, say, four to 8 weeks of studying your system? Like, how do you, I don't know, that's a hard problem, right?
It's a hard problem, but I would say if you break it down, it's just a collection of simple in quotes things which you have to do. And by now we have great tools. For example, if you take GitHub, GitHub helps you. I mean, these are tools which in the past we did ourselves and company have done themselves. They had their own tools. Now you have GitHub. For example, we do code reviews. If you have code and somebody also looks at the code, you meet, you talk about it. Actually, if you do it in the right way, it's interesting. It's not unpleasant, so that other people also get to see. Because the usual thing in research is one student writes their own code in whatever way. I mean, sometimes there are these super gifted students which write great code, but usually they just write it the way they learned or not learned it. So just there are all these standard techniques which are actually well known and established. And if you use a tool like GitHub, you have so much support. So it's work. You have to put in some effort, and it's a culture which you have to establish in your group. But I would absolutely recommend it. But it costs you a little. I mean, it's easier to produce theoretical results. You lose time if you, but I mean, yeah. What do you lose, really? I mean, if you, yeah, you gain something as well, right? In quality and practical use. Does it answer your question?
Oh yeah, hell, I mean, code reviews, an industry standard, and so yeah, for sure. Thanks for
Yeah, but it's
candor.
yeah, and just also having a culture of writing good code and understanding what it means to write good code. And yeah, because the one thing you have to avoid is a student goes away, the project is dead. You don't want that. Oh, and we also have fairly long reproducibility guidelines. So and that's a document I've written and I'm revising it all the time. These are the standards we want for your software. So for example, what I've shown you, if you have a paper, there should be a software which you can run at the click of a button and it just produces the results from the paper. It's just in my group for all students who do thesis projects with us, it's just a requirement. So it's a one-time work I had to do, write up these guidelines. And now so I have like 200 projects or something. I could go to each of them, click on a button, and then I get the result from the thesis. And this in itself, so I'm delegating this work to the students. I wrote this document once, but it's a great quality guarantee. If you do that, many mistakes can't happen because you have to make it work. So this is another thing. It's a great question. Thank you.
Thanks.
And with that, I think we should end. Jimmy had to run to teach, so he was teaching. So I'll thank you on behalf of all of us for really a fantastic talk. Thank you. And hopefully, as Charlie said at the beginning, there will come a time when we can host you here for an in-person talk.
Yeah, would be nice. Who knows?
That would be nice. Thank you again.
Thank you very much. Thank you also for the interesting questions. Thanks, and see you sometime. Thank you.